All right. So in the last class we were talking about how the power available and power required changes. So, power available is a function of speed. So, similarly we saw that my power required is also function of speed, but it also is function of altitude, and the same thing applies actually for my power available also. So, although this graph does not tell you that, but any reciprocating engine, if I go to different altitudes, my power available may actually change dramatically. Why so? I am talking about say a piston engine, reciprocating engine. Right. So, the lapse rate actually directly works for my engine also. This is with altitude. So, my power available or what the power my engine can deliver. Okay, so that is what we are talking about. My PA is basically power that my engine can deliver. So, what you can get from it. So, that is also going to drop down with and that is because I mean my air density is going to come down. But what is the solution? Can I do something about that? How can I ensure that my power available is adequate? Because more often than not, I mean especially for defense application and in particular in India, we always talk about requirements for high altitudes, because most of our borders actually are in those areas, and we have to deal with operating UAVs in such kind of challenging terrain where the density is quite significantly less. So, question is that my engine power is going to be less. If I take an engine, regular engine, I test it out here, and it is quite remarkable actually. For example, an engine let us say which is delivering maybe 2 kilowatts here at sea level. If I take this at altitude of say 15,000 feet, where my density is down by 60%, my power output will also drop by 60%, or rather it is not down by 60%, it is actually down to 60%. So, 1 becomes 0.6 density, basically specific gravity you can call it, that is 0.6, which means my power output will also be multiplied with now 0.6. So, 2 kilowatt will become 1.2 kilowatt. So, how do you solve this problem? No, but you cannot get more power. You can just ensure that the combustion is proper and you will get this entirely 1.2, but you cannot get more air. If air is less, I have to reduce my fuel, that is all I can do. If I reduce my fuel to make my mixture well balanced for proper combustion, or I can even have a system which is EFI based system. So, what happens, I mean your engines, reciprocating engines, I mean typically are of well, for one point of view they are of two kinds. One actually which has carburetor in it. Are you familiar with carburetor? Everybody knows what is carburetor's function? Mix air fuel, right. So, it is there in all our bikes, scooters, etc., all these small engines, but yeah, now I mean they are no longer there, because the recent versions of most of the scooters and bikes, they actually use EFI system. What is EFI system? Electronic fuel injection system, which electronically controls the amount of fuel which is being injected in the combustion chamber. So, it automatically ensures optimal amount of fuel air mixture. So, with that I mean I do not have to actually go and change a needle on my carburetor. So, carburetors have actually this needle settings by which you can open or close amount of fuel which comes in. Okay. So, anyway, so irrespective of that, whether I have EFI or non EFI, I mean under optimal condition my power is going to come down. EFI only ensures that it will automatically take care of that, you do not have to go and do some changing of the needle setting and so on. So, now what is the remedy? I have designed a UAV which requires say 1.5 kilowatts, okay, and for peripheral and other maneuvering requirements I have chosen an engine which can deliver me 2 kilowatts. Now, I want this UAV to fly at high altitude where my density is less, and as a result my power available for the current engine would come down to 1.2 kilowatts and not 1.5 kilowatts which I require. What happens? How do I solve this problem? Okay, that is good point. Are you familiar with turbochargers, superchargers?
Yes, sir.
Well, turbochargers require turbines. So, normal 2-stroke engine or 4-stroke engines will not have turbochargers, they will have superchargers which are separately driven, okay, by connecting to the shaft or something else, which actually would compress the air. But again, the efficiency or efficacy of these kind of systems for 2-stroke engines, which are more common for UAVs. UAVs, small UAVs, you would not find 4-stroke engines. Why? Well, more than complexity, weight. I can give you a very interesting example here. So, many of you would have driven Honda Activas. So, what is the typical cc content, the volume of the engine? 110, 120, something like that, right? Okay, so, it's a 110, 120 cc engine. So similar capacity 2-stroke engine. So, I would assume that, I mean, the 2-stroke and 4-stroke, the power is more or less same. It may not be, but let us assume it is to be same. So, if I want to make a UAV which actually uses 2-stroke engine versus a 4-stroke engine. Now, 2-stroke engine, if I want to buy a 120 cc engine, buy a popular company called Desert, something is there. Okay. So this Desert Air, I think it is called. So, they have built this 120 cc 2-stroke engine, which is very popular in fixed wing UAVs and all, and used quite a bit. You can buy a EFI, a mill grade EFI system for this. So with this, I mean, this entire thing would weigh around 2.5 kilos or something. So, roughly you are getting and the power output is around 6 odd kilowatts continuous. So, let us say if the whole setup is 3 kilos, I am almost getting 2 kilowatt per kilo or more at least. So, if I want to now bring the cost down, I thought, okay, I mean, my Honda Activa actually has an engine of similar capacity. Why don't I take that engine and put it on my UAV? It will be way cheaper, and this engine, I mean, is say $1,200. EFI system, mill grade EFI system is $20,000 for the same system. My engine is way cheaper, my EFI system is, you can do the maths, right, 1200 versus 20,000 plus. So, I mean, this from some manufacturer, some other manufacturer may have slightly lesser cost, but it is an order of magnitude more by all means. So, 2000 will become 20,000 or there about 10,000 or something like that. So when I try to inquire about the Honda Activa's engine of similar capacity and a 4-stroke one for that matter, the Activa engine turns out to be more than 10 kilos. So, low cost, but then because of certain your emission requirements, so there are more attachments inside 4-stroke system, the cooling system and everything actually. So all that actually adds weight, and it is a 4-stroke. So, 4-stroke engines are anyhow, and fuel consumption also. 2-stroke engines are very good at fuel consumption, very low fuel consumption compared to a 4-stroke one. So that way, I mean, 4-stroke engines are not viable solution as yet for small UVs, though they are available. For example, the rotary type engines. So, there is so normal engines are reciprocating type, where you have a cylinder and there is a crank moving inside that and like that. And there are rotary engines which are Wankel type, in which, I mean, the combustion is a 4-stroke engine, actually it is not a 2-stroke engine, it actually rotates. And in that itself, I mean, the compression, combustion, exhaustion, everything happens in that. So, all the 4 strokes actually happen in that rotation only. So, compared to 2-stroke engines, I mean, or sorry, compared to reciprocating engines, these engines are more popular in UAV world. These reciprocating engines are not so very popular actually in the automobile world. Why so? Because they tend to be more expensive. Apparently, probably requires more maintenance. I am not really an expert in engine, so that is the perception. But in UAV world, they are very popular. Why?
The torque is directly being transferred. So
I mean, all these are okay, but this is not the main driving force.
Compact.
No, I mean, compact I can have 4-stroke engines, or I can make compact also. I mean, like reciprocating type also I can make compact, not a really big deal.
It is slightly.
The biggest advantage is vibration. Okay. So, reciprocating engine is doing this. So, it is accelerating, decelerating so fast, so it creates tremendous amount of vibration, which actually becomes very hard for your autopilot for everything else actually. So, you have to do some all kinds of filtering, you have to do isolation, autopilot has to be mounted, and even structure, fatigue and everything. But your rotary engines, they are only spinning. So, there is some imbalance, there is some vibration, but it is much less compared to this. Yes, for reciprocating engine, they do, I mean, out of phase oscillations. So, they will take 2 engines which will, one is going 2-cylinder, they will make it 2-cylinder, one goes this way, other goes this way. So, the vibration will try to cancel out. So, this is one solution, but anyway, so we are slightly digressing, going into more depth of real practical challenges than actually the theory, which is right now the 4. So, fine. So, one solution is actually I can maybe use a turbocharger, superchargers, right. Depending on the nature of the engine, I can have a supercharger or turbocharger. Turbocharger is just driven by turbine. So, it will be more meant for a jet type engine actually. So, this is one way, and this is now going to add what to your UAV? Weight, right. So, the moment I put this, it is going to add a weight. But for two stroke systems, I am not fully aware that such optimized systems are available, which can do the compression. So, what the goal of this is that it's actually basically a compressor, which will be connected to your intake manifold of the engine, and it will deliver slightly compressed air. So, now instead of seeing the density condition of 15,000 feet or 20,000 feet, you will see a density condition probably corresponding to 6,000 feet or less, depending on how much compression you are able to achieve with that system. And it will also take power, weight and power, because you are driving something which is doing some work, it is consuming some mechanical energy. So, it will require some power also. So, that is the penalty. What is other way? Well, how else I can solve without putting anything else? Many ones. I have fuel driven, talking about replacing an engine or improving an engine so that it will work for me. Two more options are there. Well, in reality only one option is there actually, which is I can oversize my engine, and that is the big challenge actually. So, whenever we talk about putting a engine based high altitude solution, my entire UAV weight actually grows. Why? Because I have to oversize my engine. So, my engine which will normally be required for sea level would have a good power to weight ratio, but the moment I go for high altitude, my power comes down, it will degrade to almost 40-50% easily. So, my power to weight ratio is bad. So, now I would have a UAV which is carrying a heavier engine, maybe 1.5 times or 2 times heavier engine to meet the requirement. So, now instead of selecting a 2 kilowatt engine, I will probably choose a 2.5 or 3 kilowatt engine, which even at higher altitude will deliver me 1.5 kilowatt. But then this is a heavier engine. The moment my engine becomes heavier, my airframe has to become heavier to support all this. My whole structure will become heavier. UAV will be bigger and heavier. Okay. So, that is the challenge. Okay. So, that is the whole thing about my power available and power required, but how does it impact my performance? So, one key thing which actually is directly governed by all this is my excess power available, and what does it actually affect is my rate of climb. This is quite an important parameter, rate of climb. So, in this case, so we have say power available is going like this, and my power required is varying like that on this graph. So, I have power versus speed. So, whatever excess power is there at any given speed, I can utilize that to maneuver my craft or to climb, and most of the time aerial vehicles are not supposed to fly at ground level. You will fly at some cruise altitude, and that depends on your mission requirement. Okay, I want to maybe go at a longer distance, so I have to maintain enough height, so that my communication module will get direct line of sight, electronic line of sight. So, to maintain the communication link, I have to probably fly at some height. Sometimes I may have mission where I may have to avoid some being seen. So, I may want to fly very high, so that nobody can see me if I am trying to sneak on somebody. Other times my operational altitude itself may be pretty high actually. So, finally, all UAVs have to do certain amount of climbing, and therefore, this excess power actually becomes important. So, bottom line being that whatever I see as my power required for my best endurance condition, which was the minimum power, or power required for my best range condition, that is slightly more than my best endurance power, I will not select my engine based on just those two parameters. I will always keep enough margin to meet the requirements of my UAV in terms of the flight, and also cater for any additional components I may have to power, right. What else can I may need to power on my UAV? Payloads, right. So, I may have payload which may consume some power, I may be running some generator maybe to create some extra electrical energy, right, because engine is maybe driving a propeller directly, it is not giving me any electricity. I have to power my autopilot, I have to power my camera, I have to power my other peripherals which are there if I am carrying some other payload. So, I may have to even add a small generator and all. So, this excess power is used for that. But in theory right now we will simply say my power available is so much, power required at any point is so much, and this excess power divided by my weight would give me the rate of climb, right. So, this is effectively telling me what would be my vertical speed, maximum possible vertical speed. If I use the entire excess power, that is the maximum rate of climb I can achieve. If I use some part of it, then I will have some other rate of climb. So, that is why we say, so rate of climb is given as excess power that I am using divided by my gross take of weight. Okay. So, you see this is the power available, let us say, but it is actually more appropriate to say PA, because that is based on my engine power or my propeller power. Okay. So, what power my system is being able to deliver, and this is the power which I require. So, whatever delta P I have available divided by my weight gives me the rate of climb. And so, effectively you can see from this, here this is my excess power, here this is my excess power, okay. Here this is the excess power. So, you can see my excess power, so delta P is a function of V infinity, okay. So, which means my, so this is for the propeller type system, this is for the jet type system, because my power is varying like that. So, here my excess power is limited like that. So, based on that I can now plot my rate of climb as a function of speed, because my delta P is a function of speed. So, delta P by W, this is my rate of maximum excess power available at different speeds, and accordingly I will get a rate of climb as a function of speed. And from that I will see that there will be a particular speed where it is possible for me to have maximum rate of climb. So, this is my max climb rate. So, if my power available was a constant throughout, if I assume it to be a constant throughout, then my maximum rate of climb will also happen at what speed?
Maximum excess power.
What is my question? Question is, if I assume power available to remain constant, then what speed gives me max, tell me,
Speed at which power required is minimum.
exactly, right. All of you understand that? How? You see this point, right, where my power required is minimum, but yes, my power variation could be maybe skewed like this, right, if it was like that, actually I am saying, then I mean this need not be the same point. So, there is no guarantee this will be the case, only when I have a fairly flat power available, then it is a strong chance that I mean my max rate of climb will be possible at my lowest power condition, because then I have maximum difference with my power availability, okay. And you can understand, because this line is going to vary with altitude, right, and even this line may vary with altitude. So, my rate of climb will also vary. I am just drawing some arbitrary lines, it will be also function of altitude. As you climb up and up and up, my rate of climb will keep on dropping, and eventually you will reach an altitude where the rate of climb can become 0. What is that height called? Absolute ceiling. But can you reach to an absolute ceiling? No, why? What is the problem? Why can't you reach height which corresponds to the absolute ceiling of a UAV?
Run at that height.
Efficiency is different thing, but it is not possible simply because the moment you are there, your rate of climb is 0. So, how do you reach there? So, it is only a theoretical concept. So, anyway, so it is there in the next slide probably. So, let us see. Okay, this should have been there. So, let us first talk about this, then we will come back to the other things actually. So, we already talked about all these things, that my power required changes because of density requirements or density conditions rather, and similarly power available may also change with the altitude. So, there is some altitude high enough at which this graph becomes tangent to this graph. So, both the graphs are basically on top of each other more or less, or there is only one point. So, only at one particular speed, I mean you will have some rate of climb which will be eventually approach to 0. So, steady level flight is possible only at this speed. Moreover, there is 0 excess power, hence rate of climb is 0, and it may happen so that I mean your steady level flight also may be possible only at certain restricted speeds. You may not be able to fly at every speed because your power is changing with speed, right. So, it may be available only at such speed. This is called absolute ceiling, and it is only a theoretical concept. Okay. So, absolute ceiling is only a ideal or ideal concept in the sense that you would never ever reach that point. It is a limiting condition. So, you never go there, but you sort of define it like that. But what actually is more meaningful and is used for practical applications is your service ceiling, okay. Not absolute ceiling, but service ceiling. So, this is defined as the altitude where my maximum rate of climb achievable comes to 100 feet per minute. So, you can understand, I mean this have come from it is an arbitrarily defined number, it is not coming from some physical reasoning. They said okay fine, if I come up to here, that is a reasonable rate of climb and that is where I would operate. I will not want to go above this because I am getting compromised in my power available. So, 100 feet per minute comes out to be nearly half meter per second, and this is considered as a practical operational limit. So, this is my real limit in some sense. So, idea is that I mean you would not want to operate your UAV above this altitude where my max rate of climb has come to this value, and this is max rate of climb, which means this rate of climb you will only achieve at the speed where you have maximum delta power, okay, right. So, that is the idea. Any questions? All right. So that sort of covered our aspects of power for level flight, for climbing flight. Now, we will look at a condition which is gliding flight, which means no power required, 0 power condition. Most of the fixed wing UAVs which are designed to be statically stable can glide, which means if I switch off the motor, it will have some speed and it will continue to come down, descend and sort of attain an angle where it can keep on gliding actually without requiring any power, which is a good thing. Okay. So, if I switch off my power, there is no sound, nothing, I can quietly come down to some place, nobody will know that something has come and landed there. So, this could be of use, and this also is of tremendous value to solar powered UAVs for example, because they do a lot of gliding. Why? Because they have enormously long wings and at night time there is no power available. So, they would not actually consume the power, they would just glide without requiring any power. They will just power their peripherals or whatever payloads they are carrying, and instead of doing a powered flight, they prefer to do a gliding flight. So, that is the idea. So, fixed wing aerial vehicles are capable of power of gliding flight, which means your aircraft would actually have a nose down pitch attitude, and at that point it will keep on descending. So, idea is that you lose potential energy, gain kinetic energy. So, whatever potential energy you are losing, that you are using it to maintain the forward speed. So, it is 0 power condition, but the drag will still be there on the craft, and so whatever that is required, that has to be sort of balanced. So, glide is energy less flight, where if I now do a free body diagram of this, right. So, this is my airplane. So, you look at your airplane and I have weight acting here W, my drag is there, correspondingly some lift is there, and that is my horizontal line. So, the aircraft is let us say at some flight path angle theta. So, the same angle drag will have now, this angle is theta. So, what happens now? This drag is now compensated by, so I can take a vertical component here, okay, and I can take a, yeah. So, now weight I can actually resolve along this and perpendicular to this. So, this direction my weight has W sin theta component, wait, cos theta, sorry, this is theta, right. So, yeah, this is cos theta, yeah, W cos theta, and this, and I will have one along this direction, which is W sin theta. Yeah, this is correct, sorry. So, earlier I had made a wrong derivation. So, now you see this is what it is, and if I take the ratio of these two things, I can see that the tan theta equals to d by L or 1 by L by d or 1 by C L by C D. So, tan theta equals to 1 by L by d. So, higher the L by d, so if I make this L by d larger and larger, my tan theta would become smaller and smaller, theta would become smaller, because this is larger. So, my 1 by that large number will become a very small number. A small number means my angle will become small, and therefore, my glide angle would be very, very shallow. It will not glide very fast, it will glide very gently, as if like floating in the air sort of thing. Smallest equilibrium glide angle would occur at the point where my aircraft's L by D is maximized. This is the same thing which used to give me for a powered flight what condition corresponds to L by D max. In powered flight, if my L by D is maximized, what would you achieve? Best range, best endurance, or what? Range, right? Because the L by D is my propulsive efficiency of being propelled forward. Remember the term L by D is, name for L by D is, what is it? Propulsive efficiency, right? That is the name. So, if I maximize that, I will have better chance of going forward and forward and forward, which means I will have higher range. So, same thing applies here. You see, if I maximize L by D, it will correspond to maximum range for glide. Okay. Now, how much range can I cover? Okay, so, this is clear, this is simple derivation. So, effectively I would want my aircraft to operate at this condition. So, it will set some angle of attack, which would ensure I have highest possible range. So, how much range can I cover in the gliding flight? So, if I assume that my airplane is going to glide at the same angle throughout, and I start it from height of h above the ground. So, just using simple trigonometry, this tan theta would have h over range, okay, if I am going in a straight line. So, that gives me my range equals to h into L by d, which is h cot theta or h into L by d, and like I already mentioned to you, gliding flight is of quite significance for UAVs which require to remain airborne for longer periods while consuming very less power. So that is the idea. So then that is quite useful for solar powered UAVs and therefore HAPS systems, okay. High altitude pseudo satellites. Okay, so that is about the gliding flight part, okay. And yeah, so I can cover maximum range and I can really optimize it to a good extent. Okay. If I want to increase my glide time, then what do? I do not care about my range so much, right. So okay, my bad. Okay. Yeah, so this told me that I mean this L by D max gives me the highest possible range, which means during my glide I can travel the farthest. But if that does not matter to me, I simply want to increase my time, then what do? See, I would want to then operate my UAV at another angle of attack, which would maximize my L to the power 3 by 2 by D, which for a powered condition corresponds to minimum power required, right, okay, for best endurance condition. So that is what we will do here also. So you will want to then glide at a slightly different angle, which means see in both these cases you are operating at a different glide speed also, forward flight speed would be different. So if there is some way by which I can actually attain that speed and try to maintain my angle of attack around that time, which my autopilot can do all that because I have controls, right. So I can ensure that my pitch attitude is maintained at a certain angle. So that way that will ensure that I mean I can either do this best range glide or best endurance glide. So even in glide I can have this two differences. Okay. Yeah, so question is how do I establish my ceiling? We talked about ceiling, but we did not say I mean how do you establish that. It is not very tricky, it is I mean you probably already have got a sense of it. We will calculate the values of maximum rate of climb for a number of different altitudes for which I require these two things. So for my UAV, if I know okay now what happens if I have a UAV which is actually powered by a motor, electric motor, does my power available change? It does not change now, right, okay, yeah, right. So my power available would more or less not change from the motor, but my propeller's performance is still going to change, which means my power available would still change, not from the motor, but from the propeller, unless until my propeller is variable pitch. Okay. What is variable pitch? We will come to that later actually. So in the second half of the course I mean we will talk about variable pitch in a very great detail. So right now let us not worry about that, but that is the solution. If I make my propeller pitch angle more or less, I can recover some of the performance by going at higher altitude. Okay. So we will plot maximum rate of climb as a function of altitude now. So we saw we got the power available graph, we got the power required graph, and the maximum it is I will get one value of maximum rate of climb for that height. I go to some other height, look at the power available graph, power required graph, find another rate of climb, and then I start plotting that actually as a function of my height. So I will do it at not at like I mean every 100 feet, I will do it at say I can do it for 500 meters, 1000 meters, 1500 meters, 2000 or maybe even more 2 to 3000, 4000, 5000 something depending on I mean how accurately you want to extrapolate it. So we will take it up to some point, so I will get some point here, this is my calculations, right, or I can always write a code if I have all these available as a formulas or something or some functions. Otherwise I will actually calculate these at some discrete points and then finally join through a line and extrapolate it till it goes to 0. So that point becomes my absolute ceiling, and the extrapolated point where I see okay my rate of climb is now coming down to say 100 feet per minute, right. So So, that becomes my service ceiling. So, this is the approach which you have to use. Why? Because almost every operator, every user would want to know what is your ceiling of your UAV, not absolute ceiling, but service ceiling, which means this is the max altitude I can go and operate it at. So, it is very critical actually. So, this is something which has to be done for every UAV, and you have to be aware of that, and all that can be done actually using simple methods. I do not have to actually really take my UAV and go and fly it at 15,000 feet or 18,000 feet to know it. I can calculate if I have good simulation tools, or even by use these basic approaches. If I have clear characteristic of my propeller performance as a function of my density and my motor characteristic, which anyway will not change, or my engine characteristic how it is going to change with density. If I know it even at sea level, I can predict it actually by using lapse rate and all, how it is going to change with height. So, with all that information I can easily get my power available and power required at every altitude. With that I can compute this thing. So, I do not have to go anywhere, I can just use computation to predict everything, and yes, I can verify some of them by doing some experiments. So, that way I mean I can be certain that what calculation I have done, I have not made any mistake in that. Okay. So, right. So, now we have covered the conditions corresponding to best propulsive efficiency, which would give me best range, best endurance condition, which corresponds to minimum power required. But at this point we have only looked at the speeds which will give me best range and the corresponding angle of attack or corresponding L by D, and similarly we have seen what speed and corresponding angle of attack will give me the least power and the corresponding L to the power 3 by 2 by D, which I want to maximize to get lowest power condition. So, conditions we have found, okay, speed and angle of attack condition, but then how do I get my range? What is my range? How far can I go? How do I know that actually? Now, there are two things to that. One is my UAV could be, so first of course is to understand the definition, so which is written here for you. So, range, the technical definition of range is the total distance I can travel with a given tank of fuel, measured with respect to the ground. I have to know what is my distance traveled with respect to my launch point to my final landing point, traversed by the airplane on a tank of fuel, or more appropriately now on the available energy source. So, what is the farthest I can go? So, this I can calculate theoretically, but in real world I will have to define this range with consideration of my safety limits. I cannot say that I will go with 0 tank of fuel and I will try to land with that, it is not possible, and I will go to my battery going to 0 energy in that. No, I will not do that, I will have to keep some reserve. Okay. So, I will have reserve for depending on standards or requirements for some operational point of view, and for batteries I mean anyway I have to keep 20% reserve, because my battery will get damaged if I go below 20%. So, that is the reserve for battery automatically set. For fuel also I will keep some margin, and sometimes I mean for manned aerial vehicles at least they have certain standards where they will say that for after the mission, completion of the mission, you should have emergency fuel for another 15 minutes of flight. So, if you somehow end up spending more or you end up consuming more energy because there is wind, headwind or some other extraneous factors, but with all that in mind you should still have some reserve left for you to complete the mission. So, it may be specified by the user that how much reserve they want. Alright. So, that is the definition of your range. What is the definition of your endurance? The same thing, the total time that my aerial vehicle can stay in the air with given source of energy. So, distance travelled, which means distance travelled, so range will be I take off and travel, and so actually the takeoff would be more like this, I cruise climb to some height, then I descend and come back and land. Okay. So, this distance is my range. Okay. But in our theoretical calculation we will not really bother about I mean the energy spent in climbing to cruise height, but in real world you will have to. If a user gives you a particular mission that I have to take off and go 20 kilometers and deliver a payload above another 500 meters or maybe 1000 meters above your original launch point, then that means that I mean you have to factor in the energy required to climb also. Okay. But in the simple definition of range and endurance, we do not consider this extra power spent, we simply look at the end to end solution, which is theoretical number. Reality will be slightly less than that.
On the coming back of the UAV, sir,
No.
because if we define the range of a UAV is 200 kilometers.
So, range of operation is different thing. See, when you talk about your range of Airbus 320, you will not talk about, I mean, okay, it is going to go to the airport and then it has to come back. You say, what is the farthest I can go with the given tank of fuel, because all you have to do is go and land and then you will refuel there. So,
terms of UAV, sir.
no, so it does not change actually. So, see, for UAV there are, I can for my convenience define different types of ranges also. So, one range could be my communication range. Yeah, my UAV has energy that if I let it go, I do not bother about where it is going, it can probably go hundreds of kilometers, right. But then I do not have a communication equipment on board which will give me the communication for 100 kilometers. So, what I will say, actually I am not interested in sending it 100 kilometers, I only want it to operate in 10 kilometer range where I want to do surveillance, for example. So, I launch my UAV which is going and circling around in 10 kilometers and I have a communication device which gives me 10 kilometer range. So, that becomes my communication range. Similarly, I can say my operational range. So that way, I mean, it is up to me, depending on my mission, I can define different things, but the default definition of range and endurance is one way, it is just one way, okay, because you are assuming that the other way, I mean, you are going to refuel and come back. So that gives me the idea that, okay, this is the farthest I can go with this, if I am not going to return back. But for my mission, I can say my mission is not like that actually, my mission range could be different. So, what you are talking about is basically mission range, where I am saying, okay, my UAV takes off with this 50 kg payload, is my ration which I have to deliver somewhere. So, I will take off, I will go whatever x distance, drop my payload, maybe I have to bring something back from there. So, they want to send something back on the way. So, I carry that extra payload, whatever they are returning back, maybe they are giving me empty boxes. So, I take that and come back. So, my going and coming back both then have to be part of my, so it is still not defining my range, it does not change my range, it is just my operational mission. So, for any performance I can define my own mission, that okay, I want a UAV which will complete this mission, then you are actually looking at, then I am not talking about, I mean, how much energy I consume for my maximum range or something. I am simply bothered about, I mean, putting enough energy which will meet my operation, my mission. So, this is my mission basically. So, I define my mission, this is my mission and my UAV has to meet that requirement. So, you will calculate energy required for climbing, energy required for cruising, for descending flight, for hovering, if you are having a VTOL UAV which has to hover and loiter at one place, or if I am doing loitering flight using fixed wing UAV, that energy I have to find out. So, depending on the different legs of my mission, I will have different power consumption and different energy requirement. So, everything I have to add and then say, okay, this much of energy is required. So, I must put a energy source which will have capability to deliver all this energy and some margin. Okay.
We are talking that if we have given us a specification that we need a UAV for 200 kilometers,
Right.
To carry a mission,
Right.
and manufacturer is defining his range is 200 kilometers.
Right.
So, for my requirement, my UAV has to go to 200 kilometers and has to come back.
Right.
And the manufacturer is defining his range as 200 kilometers. That then both the things are not matching.
Yes, absolutely. So then I mean you have two different things basically. Okay. So your range should not say actually what your mission length is, that I have to go there and come back, or you simply say clearly I have to go here, do something, come back. Okay. So many times I mean your mission for surveillance may require that okay, I have to take off from here because I am not going to do surveillance in my area, right, I have to go in somebody else's area. So I will travel say 5 kilometers or 10 kilometers or whatever x number of kilometers, and in that area now I will loiter for say half an hour, right, I will keep looking around different places. So my range of operation is I am going to go 10 kilometers only, and then I am going to spend more time there. So, this is a very different thing. So, you cannot simply say my range is enough, then you have to define additional parameters saying that, like how often I mean we see RFPs coming out which will say, so your total time on target should be so much, where I mean you are not saying I mean I will go 500 kilometer here or sorry 500 meters here there or something, you are simply saying once I reach in my area of operation which is say 10 kilometers away, I want time on target of at least half an hour. I may do whatever I want, but I want it to stay there, then come back. So, then I mean this is a different thing. I mean if somebody is simply saying, oh my range is I mean 100 kilometers, I will fly at 100 kilometer per hour and I can have 1 hour flight time only.
This is given in SQRs.
Right. So I mean user can define their mission parameter. Now the designer okay, or a manufacturer, he may not know your exact mission requirement. So, he has designed a generic UAV which is meant for, he says I mean okay I have this thing which will fly for 2 hours.
Comparing with that, if you are not given that parameters to them, if we are just comparing that okay this
it is not easy to know actually, it's not, because traditionally range and endurance is this only, but then see for UAVs communication is very important. So, invariably everybody will define the range based on the communication range. So, they will say com range or operational range, they will say this is the range where I can operate. I may be capable of flying beyond that, but I will not communicate, so I will not go there. So, that actually sets the whole I mean your so that actually is a different term altogether. So, what we are talking about here is actually operational range, and these parameters are actually aerodynamic range basically or my performance range, and these are coming from fixed I mean your manned aerial vehicle world, not so uncrewed or unmanned type. And like we said that I mean we already have seen that my flight condition for best range and endurance is not same. So, simultaneously I cannot say that I mean I am flying at a speed which will give me the maximum range and also maximum flight time, no. I can either fly with a maximum range condition or I can fly with a maximum endurance condition. So, they are both going to be different, and they will also be different for propeller versus jet powered aircrafts, like the speeds that they would typically have. So, now with this given energy source part makes critical change in the way we work. Why? Because traditionally these formulas for range and endurance which are there in all these textbooks, like if you go and look at our basic textbook here which is Anderson's book, you will see he will derive your condition for or formulas for highest range possible or highest endurance possible by assuming that the craft is powered by a fuel based system. So, he has a tank of fuel and these fuel tanks actually carry significant amount of fuel. So, if I assume it that with time it is going to get consumed, it actually does change my power required, because my overall weight will keep on decreasing. But when I do it with a battery powered system, you do not have that luxury. So, going and coming you are the same, I mean however far you go, you are only consuming the energy and not the weight. So, my weight remains constant, which makes my formula very simple actually. If I am going at a particular speed, my range is simply and this is my power consumption, it is simply power into time and velocity into time. I go at a fixed speed and my takeoff weight does not change, so my power required does not change. So, it is just a very simple calculation. But what we look at is actually for a engine based system, and for engine based system we also need to define this particular parameter called specific fuel consumption. So, the critical factor influencing range and endurance is this new parameter which is a characteristic of the engine, specific fuel consumption, which is what I said. For a reciprocating engine, specific fuel consumption, which we abbreviate as SFC, or people often write it with a symbol small c, is defined as weight of fuel consumed per unit power per unit time for reciprocating engines, which comes out like this. So, we will say my SFC of a 2-stroke small engine is say 1 kilogram of fuel per kilowatt per hour, which means if I take that engine to power a system which is consuming say 2 kilowatts, then every hour you are going to consume 2 kg of fuel if my SFC was 1. And if I operate this thing for 3 hours, then my total fuel consumption will be 6 kgs. But this is actually called inconsistent unit. Why? Because I mean weight is defined in newtons in SI units, right, and your power is in joules per second, that is the correct SI unit, and your time is in seconds. So, when you are using it in formula, you have to convert it into this unit, but a engine manufacturer, for ease of remembering the number, for ease of handling, ease of bookkeeping, he will give you in this unit. So, the 2 stroke engines, small engines, like we have been using 3.5 HP engines, 2 stroke engines, we have used more 7 or 8 HP engines also, and typically all these engines would have almost similar ballpark SFC, which is around 0.6 kilogram per kilowatt hour, which means if I consume 1 kilowatt, my engine is delivering 1 kilowatt, it will consume 600 grams of fuel, which means what is the volume? This is not the volume of the fuel, because you will have to decide the fuel tank also for your UAV, because depending on how much. So, the specific gravity is 0.8 roughly, right. So, which means 1 liter of fuel weighs 800 grams, which means 600 grams is slightly less, it will be how much. So, 1 liter of fuel weighs 0.8 kilo, right, which means 1 kg of fuel would weigh 1 by 0.8 liters, or rather would require this much volume, which means 0.6 kg is 0.6 by 0.8, which is 3 by 4th of a liter. So, it will consume 3/4 of a liter every hour for 1 kilowatt consumption. If my engine draws 2 kilowatt of power, then it will consume almost 1.5 liter every hour, like that. So, normally your engine manufacturer will give you this. So, when you are selecting your engine, you can look at this number and then you can immediately see how much your power is required, which we have already done earlier based on my drag profile with my drag bucket and everything, or drag polar. So, I will be able to get my power required, and therefore, I will be able to see my fuel consumption, how much I am going to burn. So, now depending on my mission energy requirement, I have to fly for 2 hours, 3 hours or whatever, I will put that in here. Yeah. So, these are the 2 units. So, this is what you use in the formula. This is what manufacturer will give you. So, you have to do the appropriate unit conversion before you put in, but which formulas, let us see. Yeah. So, let us, if I want to look at the condition corresponding to maximum endurance for a propeller UAV, in order to stay in air for longest period of time, we must use minimum weight of fuel per hour, which means minimum power consumption, because power consumption and fuel consumption are proportional, we saw already. So, maximum endurance for a propeller driven airplane occurs when it is flying at minimum power required, which in this power graph corresponds to this point of minimum power, of min power, right, and this corresponds to the point where my CL to the power 3 by 2 by CD is maximized. So, now how do I calculate the endurance? So, this formulas for range and endurance was calculated long ago by French engineer Louis Breguet, and you will come across his name. So, these formulas are called Breguet formula for range, at least for the range. Endurance one, probably I do not recall whether he was the person who did the endurance one also, but range formula is called Louis Breguet formula for range. and Louis Breguet was actually an aviation pioneer. He worked on fixed wing side also a little bit and a lot on actually rotary wing side. He was trying to build a helicopter long ago. So, we define certain definitions here. Why? Because my UAV is driven by a fuel system and my fuel will get consumed, and we saw my fuel consumption would be quite significant. I mean 600 grams per hour per kilowatt or thereabout for a 2-stroke engine, small 2-stroke engine, and this small UAV would be maybe weighing say 20 kilos, 25 kilos, but it may be carrying I mean 4-5 kilo of fuel. So, you can understand if that kind of system I mean which is weighing 20 kilo is consuming 4 kilo of fuel, there is a significant change in the weight with every passing hour, which means my power required is also going to change continuously, right. So, that is what we are doing here. So, we will say W naught is my gross weight of the airplane, weight with full fuel, payload, everything, gross takeoff weight, that is my GTOW. W naught is GTOW, and I am carrying weight of my fuel weight, which is significant. The longer the mission, the more is the fuel weight. If you want to fly farther and farther, you will have significant amount of fuel weight. See, there are Sayed drones which are traveling 1500 kilometers, okay, and they are barely carrying 8 to 10 kg of payload. So, if they are carrying I mean going 1000 kilometers, then the bulk of I think 1/3 or at least I mean 20 to 30% of the weight of the craft would be fuel weight, if not more easily fuel weight. And finally, W1 is sort of my empty weight, which is weight without fuel. So, W1 is equal to W naught minus my weight of the fuel. So, this is my craft weight without my fuel weight, and we can sort of go back and look at my definition of my, what is my C? SFC, right. Okay. We said I mean SFC we can use symbol C also. So, this equation allows me to take a derivative of this equation, that is how my weight is changing. See, all these weights are changing except my W1, right. So, my W1 is not changing, W1 is without fuel. So, that is the fixed weight. W naught is changing and my WF is changing. So, how at what rate my WF is changing, it is dependent on my power and my SFC, right. So, this basically tells me that the rate at which a rate of change of fuel weight is given by this expression, which depends on my SFC and my power consumption. Okay. And so, with this I can write the equation in a slightly different manner, which is dt equal to minus of dw by Cp, and once I get this equation I can integrate that, because I want to know the time, how long I can fly. So, my time of flight from 0 to end or till my endurance, max endurance E, and during this period my weight is going to change from W naught to W1. So, with this kind of condition I can do this integration, and so finally on this side I have my E, which is my endurance, is equal to integral of, yeah. So, this is actually with the minus sign. So, W0 to W1 I can use this minus inside and flip the limits of integration. It is either way, it is one and the same thing. Why? Because this also makes sense, because my W1 is a lower weight, W0 is my higher number, right. So, W1 goes on top, W1 is at the bottom. So, this is what is the basic formula to calculate my endurance. So, I will stop here, because we can look at the range in the next class, it will take some time. So, this is now I mean I need to know how my power is going to change as a function of weight, right, because now my power is not constant. So, we need to calculate this integral, we need to know how P required changes with weight. Okay. And we will in the next class we will try to get the expression for this also. But remember, this is only for UAVs which are driven by fuel. I will also do the simple derivation for your system with battery, which is actually trivial. There is no formula, nothing to be done. I mean, because your P is constant, because your weight is constant, and if P is constant, then your total battery energy capacity we can look at. So, P into time will be my basically energy capacity of my battery. So, I can simply get the time of flight from that. Okay. So, we will stop here. We will understand the definition of range again for a fuel driven system first, and we will try to get some notation for both of these things actually. And if you have any queries for your homework assignments, you can send it through email, or you can send me WhatsApp message. I will try to answer those questions. Okay. It is due on the next, when it is due? Tomorrow it is due. No, I mean the time is set anyway on the, you have to submit in the class, right? Okay. Oh, sorry, I mentioned, okay, I forgot. Okay, I mentioned it to be submitted to the lab, okay, because tomorrow I am not there in the lab. So, when you enter the helicopter building, on the ground floor there is office. So, you have to go and submit it there, okay. But that is only up to evening. By 5 o'clock the office will be closed. Okay. So, make sure you go and submit it by evening 5 o'clock. Okay. So, if you have any questions remaining, ask it today itself, do not wait for tomorrow, fine.